Good morning. In yesterday's lecture, we were discussing the evolution of a disturbance in an elastic medium, an elastic rod, let us say. And the kind of disturbance that we were discussing, we had a deformation of the rod, and we considered the situation where the deformation, we studied the evolution of the deformation in the same direction as the deformation itself, and we had obtained an equation which governs the evolution of disturbances in an elastic rod. So the disturbance was xi, the variable xi represents the displacement of any element of the elastic material, and these displacements are along the x axis, and we had assumed that the displacements also vary only along the x axis. So the xi is a function of x. The only spatial variable that xi is a function of is x, and it is a function of t also. And we had obtained this differential equation, this partial differential equation, which governs the evolution of xi, and this partial differential equation we had written in this fashion, where we had this constant Cs, which was the square root of the Young's modulus divided by the density of the elastic medium. And I had told you that this equation is the wave equation. If we have a disturbance which can propagate, which varies in all three directions, then you have to replace then you have to replace the derivative with respect to y with the Laplacian operator, that is del x square plus del y square plus del z square, and the wave equation is now given by this. Now I should tell you the first thing that I should tell you is that the waves which we had considered in the last class are what are known as longitudinal waves. So the waves that we had considered in the last class are what are known as longitudinal waves. What do we mean by longitudinal waves? A wave is said to be longitudinal if the disturbance in this case the disturbance is along the x axis, the displacement of any point in the elastic medium xi is along the x axis, and xi itself varies along the x axis. So such a wave is said to be a longitudinal wave. You could also have another kind of wave called a transverse wave. Let me give you an example of a transverse wave. If we have a stretched string, so think of this line as a string which has been pulled tight, it is stretched, and if in this string we introduce a disturbance which is perpendicular to the direction of the string, let us say that I plug the string like this and leave it, then the evolution of this disturbance is a transverse disturbance. It is this disturbance is going to move around along the x direction, and if I use the same symbol xi to denote the disturbance is perpendicular to the direction in which the wave can propagate. So this is called a transverse wave. Another situation where we have a transverse wave is the electromagnetic wave. And I have already told you that for an electromagnetic wave, if I have electromagnetic wave is a disturbance in the electric and magnetic field, and if this is the disturbance in the electric field, then if I have a wave which is propagating in this direction, the electric field disturbance can only be in the directions perpendicular to the direction in which the wave is propagating. This too is a transverse wave. The electric field and the magnetic field both have to be perpendicular to the direction in which the wave is propagating. So if the wave is going along the x-axis, which is the situation that we have been discussing, the electric field can be anywhere in the yz plane. So both of these are transverse waves. So we have different kinds of waves possible. We have longitudinal waves possible. We derived the wave equation for a longitudinal wave, which is disturbances in an elastic medium, longitudinal disturbances in an elastic medium. But you could also have transverse waves like the disturbances in a string. Now in all such situations, the evolution of the disturbance is typically governed by such a wave equation. So the wave equation that we have derived is very general. It does not hold just, it is not that it holds just for the elastic waves, it holds in such an equation arises in a large variety of situations. So if you analyze the evolution of the disturbance in the string, or if you analyze the evolution of the disturbances in the electromagnetic field, in all situations you will find that the disturbance is governed, the evolution of the disturbance is governed by such a wave equation. The only difference that occurs when I go from one kind of wave to another, the main difference that occurs is that the speed at which the wave propagates, the phase velocity of the wave, that changes. So for an elastic wave, we found that the phase velocity of the wave is related to the properties of the elastic medium. It is the Young's modulus divided by the density. If I have some other kind of wave, if I have wave disturbances in a stretched string, then this phase velocity is the square root of the tension per unit length of, so this will be replaced by the tension divided by the mass per unit length of the string. For an electromagnetic wave, it is the speed at which speed of light in vacuum, and so forth. So depending on the particular wave that you are considering, the value of this constant, the value of the phase velocity will be different, but usually the wave is, you will find that the wave is governed by an equation like this. So this kind of an equation is a very general equation, and it arises in a large variety of situations. So it is very important to understand the solutions of the wave equation, which is what we are going to discuss in today's lecture. Now I have already also told you that that the sinusoidal plane wave, which we have discussed at great length earlier on in this course, the sinusoidal plane wave, which can be mathematically expressed like this, I have shown you that the sinusoidal plane wave is indeed a solution to this wave equation. So this is indeed a solution to the wave equation, provided the wave number k, the wave number corresponding to this wave vector, and the angular frequency are related in this fashion. So the relation between the angular velocity and the wave number is called the dispersion relation. So provided the angular velocity and the wave number satisfy the dispersion relation corresponding to this particular wave, so the dispersion relation for this particular wave will have the phase velocity, the constant c which occurs here, appearing in the dispersion relation. So provided omega and k are related like this, then this is a solution to this wave equation. So we have already seen one particular solution, a special solution to the wave equation. Now let us discuss a more general kind of a solution of the wave equation. So the first kind of solution that we shall discuss is called a plane wave solution. So let us discuss a plane wave solution of the wave equation. What do we mean by a plane wave solution? We are going to assume that xi, the disturbance, which in general could be a function of all three spatial variables x, y, z, we are going to assume that it depends on only a single spatial variable. So the xi, the disturbance, varies only in a particular direction, and we will use x to denote that direction. So we will assume that xi, the disturbance that whose evolution we are studying, could be the longitudinal disturbances in an elastic rod, could be the transverse vibrations of a string. Whatever it be, we will assume that it depends only on x, not on y and z. Now, if the disturbance depends only on x, let me draw the x, y, z coordinate system. This is x, this is y, and this is z. Rather, let me put it other way around. This is z and this is y. So we have a right-handed coordinate system. And if you impose the condition that xi depends only on x, then you see that the value of xi is a constant on a plane which is parallel to the yz plane. So it is constant on this plane. It will be constant on this plane also. It will have a different value on these two planes. So xi, if it is a function of x alone, will be constant on this plane, it will be constant on this plane. The value of xi could be different here, and it will be different on every other plane in between. Since the value of xi is constant on planes, this is referred to as a plane wave solution. So that is the first point which you should note. So when we speak of a plane wave solution, what we mean is that the value of xi is constant on planes, and in this case the planes are perpendicular to the yz plane. If instead of x I had chosen y, then the planes would be perpendicular to the xz plane, and so forth. So in this situation, when xi is a function of x alone, the wave equation that we have to deal with is this. It is you have the second partial derivative with respect to x of xi minus 1 by c square. Now please note that I am going to use c without the subscript x to denote the speed of the phase velocity of the wave. So I am not going to put the s explicitly in all of today's lecture. So you should realize that the c which is here is not necessarily the speed of light, it is the speed of light in vacuum when we refer to an electromagnetic wave. When you are dealing with an elastic wave, c is the speed, the phase velocity of in the elastic medium, which is the square root of y by rho, etc. So c is the phase velocity of that particular wave, not necessarily the speed of light in vacuum. It is the same as this cs, just that I am not going to show this s explicitly. So the wave equation is this minus 1 by c square del by del, the partial derivative of with respect to t, this is equal to 0. Xi is a function of x and t, and we are looking for solutions to this equation. It is convenient to introduce two new variables, w1, which is x plus ct, and w2, x minus ct. So xi now is a function of w1 and w2. We can replace these two variables x and t, position and time, with the two new variables w1 and w2. So we have to also now replace the derivatives with respect to x with derivatives in terms of w1 and w2. So let me work out the derivative of with respect to x in terms of derivatives with respect to w1 and w2. So del x is equal to del w1 So the derivative with respect to x, the partial derivative with respect to x, you can express in terms of partial derivatives with respect to w1 and w2 using the chain rule of differentiation. And so you have to now calculate these derivatives, the derivative of w1 with respect to x, the derivative of w2 with respect to x. So let us go back to our expression for w1. If you differentiate this with respect to x, you get 1. Similarly, if you take the partial derivative of this with respect to x, you get 1. So you find that this is equal to this. So the derivative with respect to x can be written in terms of derivatives with respect to w1 and w2 like this. Now let us also work out the derivatives with respect to t. So the quantity which is convenient to deal with is 1 by c partial derivative with respect to t. Again we will do the same thing. So I will put a 1 by c here, del w1 del t del w1 plus 1 by c w2 del t So we have now, what we are doing is we are expressing the derivative with respect to t, the partial derivative with respect to t in terms of partial derivatives with respect to the new variables w1 and w2. So we have to calculate this partial derivative first. So what happens when I differentiate this with respect to t and divide by c, I get plus 1. If I differentiate this with respect to t and divide by c, I will get minus 1. So we see that this is equal to So we have worked out the derivative with respect to x and t in terms of derivatives with respect to the new variables w1 and w2. Let us now go back to our wave equation. So this is the wave equation we originally started with. In this wave equation, we have to now replace derivative with respect to x in terms of the derivative with respect to w1 and w2. We also have to replace derivatives with respect to t in terms of derivatives with respect to w1 and w2. So we have to square this. So when you replace, let me do it for you explicitly instead of it's quite straightforward. So the derivative with respect to x, the equation that we get is the derivative with respect to x squared. So we have partial derivative with respect to w1 plus partial derivative with respect to w2, that's the derivative with respect to x, the square of this acting on xi. So I have written down the first term over here, the square of this operator, that's the partial derivative with respect to x, this acting on xi, and then I have to subtract out this. So I have to subtract out, So I have to subtract out del w1 minus the partial derivative with respect to w2 square into xi. This is equal to 0. This is the equation. This is the same wave equation. So what we have done is we have written this wave equation in terms of derivatives with respect to w1 and w2. This is the derivative with respect to x, which has been written like this. This is the derivative with respect to t divided by c square, the second derivative, which I have written in this fashion. So the same wave equation is now this equation over here in terms of w1 and w2. Now when I expand out the first term, let me expand out the first term. So when I expand out the first term, what I get is partial derivative with respect to w1, the square of this, plus 2 times partial derivative with respect to w1 and w2, which is the cross term between this and this, plus the square of the second term, this whole thing acting on xi, minus, now when I square this, I will have I will get the same thing as this, but with an extra minus sign, because there is a minus sign over here. So I will have minus 2 del square plus this acting on psi is equal to 0. Now when you add these two terms, there is a relative minus sign here, so this will cancel out with this will cancel out with this, and you are left with the equation that you are left with. Let me so the equation that you are left with is that the second derivative of psi, which is a function of W1 and W2 with respect to W1, this is equal to 0. So what we have done is we have changed variables. We started off with psi as a function of x and t. We have changed variables, gone over to two new variables, W1 and W2, and we have written the wave equation in terms of these two new variables, and this is the equation that we get. We have to now look for solutions to this equation. Now you see that this equation, finding the solutions to this equation is much simpler. You can guess the solutions to this equation, much simpler than the original equation that we had, and there are three possibilities you can straight away think of. The first possibility is if psi W1 W2 is a constant, but this possibility doesn't give us a propagating disturbance. It's not a wave, so it's not a very interesting solution, though it's a mathematically permissible solution. The second possibility, which is interesting now, is a situation where psi is a function, some arbitrary function of W1 alone. So if psi is a function of W1 alone, the function should be differentiable, and we would like the function to vanish at infinity, plus minus infinity. Otherwise there is no other restriction. So if we choose psi to be a function of W1 alone, then when you put this here, the derivative with respect to W2 is 0, so this equation is satisfied. So this is, you see, this gives you a possible solution to this equation, and you have another possible solution, which is the situation where psi is some other function f2 of W2 alone. So if we have some arbitrary function of W1 alone or some arbitrary function of W2 alone, then both of these are solutions to the wave equation. So let us go back to the variables which we started out with. So what we see is that the solution to the wave equation can be written in the following way. It could be some arbitrary function f1 of W1, and W1 is x plus ct, plus some other arbitrary function f2 of W2, which is x minus ct, and this combination, linear superposition of two such functions, is a solution to the to this wave equation for which you are trying to find a solution. So we have obtained the most general plane wave solution to the wave equation, planar solution to the wave equation. Now let us interpret this solution. Let us first focus on a situation where we have only the first function. So we have only, let us focus on this particular solution. Let us set this to be 0, and let us focus on this particular solution. So at t equal to 0, let us plot this function. f1 could be some arbitrary function which is differentiable, and we would like it to vanish far away. So let me plot some such function. You could choose any function that you wish. So I will ask you to plot a function of your choice. I will plot a function of my choice. So let me plot a function. So the function that I will plot looks something like this. So at t equal to 0, the function looks like this. So this is f1 x, which is xi at t equal to 0. We have only this, we do not have this part, we are not considering this part, we are only considering this part. So, xi at t equal to 0, xi is f1x, which looks like this, some arbitrary, you could choose some other function which you prefer for your of your choice and draw it. So, now we have drawn xi at t equal to 0. Now, let us ask the question, what will xi look like at t equal to 1? Let us ask the question that xi has a particular value f1 0 at this point at t equal to 0. Where will xi have the same value at the time t equal to 1? So, at t equal to 1, we have to make the argument of this function the same as x as 0. We have to make the argument of this function 0. So, what you see is that the argument of the function becomes 0 at the point x is equal to minus c at the time t equal to 1. The argument of this function becomes 0 when x is equal to minus c. So, this kind of an argument applies to all the points. So, what you can say is that the whole function at the time t equal to 1, the whole function has shifted by the amount c, the whole function has shifted to the left side. So, the whole function has shifted by an amount x equal to minus c. That is what happens as time evolves. So, at time t equal to 1, the whole function has shifted. So, we have exactly the same thing repeated, but it is now all shifted by an amount which is equal to c. At t equal to 1, the whole thing has shifted by an amount c to the left. At t equal to 2, so at t equal to 2, if you ask the question, where is the value of xi the same as the value as it was at this point at t equal to 0. So, you want to make the argument of this function 0 at the instant t equal to 2. So, this is going to happen at x is equal to minus 2c. So, what you see is that at t equal to 2, the whole curve has shifted by minus 2c. So, it has shifted to the left by 2c. So, at t equal to 2, the same curve is going to be the value, it's going to be the same curve, the value of xi is going to be described by the same curve. All that has happened is that the curve has shifted by an amount 2c to the left. So, what we see is that this part of the solution represents a wave propagating to the left at the speed c. Let me repeat again, we have determined a general solution to the wave equation, and the general solution we found is a sum of two parts. The first part is some arbitrary function of x plus ct, the second part is some arbitrary function of x minus ct. We have been interpreting the significance of the first part, which is some arbitrary function of x plus ct, and what we saw was that this corresponds to a wave propagating to the left with the speed c. So, the functional form of xi does not change, all that happens is that it keeps on shifting to the left. So, this picture over here shows you the evolution of the left propagating plane wave solution. So, this is the solution at t equal to 0. At t equal to 1, the whole solution has shifted to the left, and at t equal to 2, it has shifted further to the left, the shift being, so from here to here the shift is going to be c, from here to here the shift is going to be 2c, and at t equal to 3 it would have shifted 3c. This shows you an animation of the left propagating plane wave. So, this, and it keeps on moving as time evolves. So, let me show you this again. So, as time evolves, this is xi at t equal to 0. At t equal to 0, xi is the function fx. f1x in this case, and then as time evolves the whole pattern moves to the left with the speed c, which is what you see here. So this part of the solution represents a wave propagating to the left. It's a left propagating wave. Now you could ask the same question, what does this part of the solution represent? And it is quite clear what this part of the solution represents. f2 again could be some arbitrary function, and as time evolves, so at t equal to 0 the xi x, let us forget about this and focus only on this. At t equal to 0 xi x is f2x. As time evolves the whole pattern now propagates to the right with the speed c, which is what you can, this picture shows you. So we have f2 which is some other function, some arbitrary function of x. This is the functional form at t equal to 0. As time evolves, so this is the whole thing shifts to the right. So this is the functional form of xi at t equal to 1, and this is the functional form of xi at t equal to 2. So this shows you an animation of how a right propagating plane wave evolves. So this shows you xi as a function of x at t equal to 0. It is described by a function f2x. At t equal to 1, 2, 3, the whole thing keeps on shifting as time evolves, and it shifts forward in x with the same speed c. So let me just recapitulate what we have done. We wanted to look for solutions of the wave equation. The disturbance, the wave disturbance xi could in principle be a function of all three spatial coordinates x, y, z. We restricted our attention to a particular situation where xi depends on only one spatial coordinate, and we chose it to be x. So xi is constant on planes perpendicular to the x axis. This is called a plane wave, and we found solutions to the plane wave equation, and we found that there are two kinds of solutions possible. The first kind of a solution is could be some arbitrary function of x plus ct. This represents a wave propagating to the left, or it could be some other arbitrary function of x minus ct, which represents a wave propagating to the right. And in general, any arbitrary solution could be a linear superposition of two such functions. Now the plane wave, the sinusoidal plane wave, which we have discussed extensively earlier, the sinusoidal plane wave in purely real notation can be represented like this: a sine omega t minus kx. This is a sinusoidal plane wave which we are already quite familiar with. Now let us check that the sinusoidal plane wave is a special case of this solution. So to show you that, all that we have to do is we have to choose the function f2 to be a sin x. So with that choice, so I have set f2 to be a sin x. So with this choice, sin x into kx. So let me write it here, f2. I have chosen f2 to be a sin kx. Then the solution xi with this choice of f2, the solution xi is going to be f2 of the function of x minus ct. So it will be a k x minus ct, which we see is exactly the same as this. provided we identify I could put a minus sign here, so this will be minus, and I have minus here. So this is exactly the same as this. This represents a left propagating wave, and all that you have to do is you have to identify omega, the angular frequency, with k into the speed c. So what we see is that the sinusoidal plane wave, which we have been discussing, is a particular example of a plane wave solution where the function is a sine, but you could have a much more general solution, and any arbitrary function, provided it vanishes far away, vanishes at infinity, and or it is well behaved at infinity, need not vanish. Sin x does not vanish. So provided the function is well behaved at infinity and it is differentiable, then it could be a solution, right. So this is a very special solution where this is a sine function, but in principle it could be any arbitrary function, provided it is well behaved at infinity, well behaved everywhere, and it is differentiable everywhere. So these were the plane wave solutions to the wave equation. Now we will discuss another kind of solution today. So the other kind of solution that we are going to discuss is what is called a spherical wave solution. So the next kind of solution that we are going to discuss, spherical wave. So we are looking for solutions to the wave equation. So let me show you the wave equation again. We are looking for solutions to the wave equation. This is the wave equation, and xi could be a function of all three spatial variables x, y, z, and time. Now we are again going to impose a certain symmetry. The plane wave solution comes when you impose a planar symmetry. We are again going to impose a symmetry. We are going to assume that xi depends only on the distance from the origin. So we have chosen a particular coordinate system x, y, z, and this is the origin of the coordinate system. We will assume that the wave, that we have a situation where the value of the wave disturbance depends only on the distance r from the origin. So this is the distance r from the origin. We will assume that xi depends only on this. So xi has constant value on spheres centered on the origin. So the value of xi is the same on this. Xi will have a different value on this sphere, but it will be same all over the sphere. So depending on the radius of the sphere, xi will have a different value. So we are assuming that xi depends only on the distance from some fixed point, which is the origin. So this is the value of xi is constant on spheres, so that's why it's called a spherical wave solution, spherical wave. Now I'm sure you are familiar with the spherical polar coordinate system. So the spherical polar coordinate system has three variables, r, theta, and phi. Instead of using the Cartesian coordinates x, y, and z, it is equally possible to equally well describe this whole space, all points in this space, using a spherical polar coordinate system r, theta, and phi. So you could suppose we are using a spherical polar coordinate system, so we don't have x, y, we are not using x, y, z, we are using r, theta, and phi. The question now is that we have to represent the Laplacian operator. The Laplacian operator, you know, is the sum of partial derivatives. So the Laplacian operator is the second partial derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. So the Laplacian operator is this sum, it has derivatives with respect to x, y, z. When you go over to this spherical polar coordinate system r, theta and phi, you have to represent this Laplacian operator in terms of derivatives, not in terms of x, y and z, but derivatives in terms of with respect to r, theta and phi. So briefly, you have to now write down x, y and z in terms of r, theta, phi, and then transform these expressions just like we wrote it in terms of W1 and W2. You have to use the chain rule of differentiation and write this in terms of derivatives with respect to this. Now I shall not go through the algebra, it's a little tedious and lengthy, so I shall not go through the algebra, but the point is that it is possible to write down the Laplacian in terms of the polar spherical polar coordinate system, and you will have terms involving derivatives of r, derivatives of theta and derivatives of phi. Now the equation which we are trying to solve is this, the Laplacian of xi minus 1 by c square time derivative of xi. So when you have the Laplacian acting on xi, remember that xi is been assumed to be a function of r alone. So when the Laplacian acts on xi, the derivatives with respect to theta and derivatives with respect to phi are not going to matter. It is only the terms involving derivatives with respect to r which are going to be important. So I can write down the Laplacian. The point is that I can write down this in the spherical polar coordinate system, and if in general the Laplacian in the spherical polar coordinate system will have derivatives with respect to r, derivatives with respect to theta and derivatives with respect to phi. You can get the expression in any book on mathematical physics or any book, let's say, on electrodynamics, but the point here is that the derivatives with respect to theta and phi are not going to be important because we are assuming that xi does not depend on theta and phi, it depends on r alone. Theta and phi refer to different points on the sphere. We have assumed that xi has a constant value on the sphere. So it is only the r derivatives that we have to retain. We can ignore the theta and phi derivatives in the Laplacian, and if you retain only the r derivative, the Laplacian is 1 by r square del r, partial derivative with respect to r square partial derivative with respect to r of xi. So this is the Laplacian written in the spherical polar coordinate system. So you have derivatives not of x, y, z, but with respect to r, theta and phi, and we have dropped the terms involving derivatives with respect to theta and phi. So this is what the Laplacian operator acting on xi becomes. Now we replace this in the wave equation. So the wave equation now reads as follows. So for a spherical wave, the wave equation now becomes 1 by r square partial derivative with respect to r, and then I have r square partial derivative with respect to r xi minus 1 by c square partial derivative with respect to t square of xi. This is equal to 0. We are looking for solutions to this equation. Xi is a function of r and t. Now it is convenient to introduce a new variable here. So xi is a function of r and t. It is convenient to introduce a new variable u, which is also a function of r and t, such that xi is equal to u divided by r. So with this new function, introducing this new function, we have to differentiate this once with respect to r. So let me do it here. 1 by r partial derivative with respect to r, and then I have r square, and let me write down the derivative of xi with respect to r. So I will have one term which is the derivative of u divided by r, and I will have one term which is the derivative of r. So I am going to get u divided by r square. This is the first derivative of xi. This minus the term over here, which I am not going to write down explicitly again, I am just indicating it. Okay, so this is the same time derivative term which is here. Just that you have to replace xi in terms of u. Now you can simplify this term. So what will happen is that this factor of 1 by r, so let me write it here, 1 by r and I have r into del u del r minus u, that's what we have, minus again the time derivative, I am just carrying it unchanged, is equal to 0. So this is the same thing as this. Now we have to differentiate it with respect to r again. Notice that if when I act on this, I will get two terms. One term is the derivative of r into, so which is 1. So one term is going to be del u del r, which is exactly going to cancel out with the term that I get when I differentiate this. So there is only finally one term which remains, which is r into the second derivative of u. So we can now write down the same equation here. So what we have is 1 by r square and r into the second derivative of u. So this is what you get from this whole term over here, and I have to also write down this term over here, replacing xi with u by r. So r 1 by r comes out, and what I have is minus 1 by c square 1 by r del u del t square is equal to 0, and the factor of 1 by r gets cancelled out, and finally what we have is del u del r square minus 1 by c square del square u del t square is equal to 0. So what you see is that u, the new variable u which you have introduced, satisfies exactly the same wave equation, the same one-dimensional wave equation which we have just solved earlier, and we have seen that there are going to be two solutions. So I can straight away write down the solutions for u. U as a function of r and t is going to be a sum of two solutions. The first part is f1 r plus ct plus f2 r minus ct. We have already studied the solution to this wave equation, which is what I have written down here, and then I can straight away write down xi as a function of r and t. This is going to be f1 r plus ct divided by r plus f2 r minus ct divided by r. So we have worked out the spherical wave solutions, and again we see that the spherical wave solutions are a sum of two parts. That it could be some arbitrary function f1, well behaved arbitrary function whose derivatives are also defined, of r plus ct divided by r plus some other arbitrary function of r minus ct divided by r. So we have two possible solutions. Now remember that r is, if this is the origin, r is the radial coordinate, so r changes in this direction. So as you go from this sphere to this sphere, the value of r increases. So for a plane wave, these two solutions corresponded to left and right propagating waves. In this particular case, just see, as t increases, the value of r has to go down. If you are following the point where f has a certain value, where this has a certain value, the value of r has to go down. So this represents a wave which is propagating inwards. So the first part represents a wave which is propagating inwards, that is decreasing r. The second part represents a wave which is propagating outwards, that is increasing r. Now a point to note here is that as the wave propagates inwards or outwards, its amplitude changes as 1 by r. So if you have an outward propagating wave, outward means as time increases r increases. If you have an outward propagating wave, this represents an outward propagating wave. As time increases, the wave goes in this way, the value of r increases, and as the wave propagates outward, its amplitude falls as 1 by r. Okay, so let me show you an outward propagating wave over here. So the value of the wave has a fixed value on this sphere at some time. At a later time, that same value has shifted out, but the amplitude has fallen by 1 by r. And then at a later time, the whole thing is again shifted out, the amplitude falls again as 1 by r, and the amplitude keeps on falling as 1 by r. Okay, so this is an outward propagating wave. And if you want to see an inward propagating wave, this shows you an inward propagating wave. Now we could ask the question, in what context do we have outward and inward propagating waves? Now if I had a point source from which there is some wave coming out, so there is a source which is localized at a point and there is some wave coming out from that, well, this could be represented using the outward spherical solution. So this will represent such a solution. So if I have a source located at the center over here, so let me show you this. So if I had a source located at the center, over here, and there was a wave coming out from this, the evolution of the wave would be described by an outward going wave. So as time evolves, the wave would get evolved into larger and larger spheres like this, and the amplitude would fall as 1 by r. Or if you ask the question, how does the intensity fall, the intensity would fall as the intensity goes as the square of the amplitude, so the intensity would fall as 1 by r square. So this is the outward propagating wave. The inward propagating wave, it also has applications. Suppose I send light through a lens which focuses the light to a point. Then once the light comes out from the lens, I can represent it by a spherical wave, and that spherical wave is going to slowly, that sphere is going to slowly contract. It's an inward going wave. The intensity of the light is going to go up, and at the focus it's going to go to infinity. Okay, and then the light is going to go through the focus. So the light is going towards the focus, and then it's going to go through the focus and it's going to come out. So the inward going wave is going to collapse, and then it's going to come out as an outward going wave. Okay, so in today's lecture we have discussed solutions of the wave equation. The wave equation itself is very general. It appears in a large variety of situations, and in today's lecture we have discussed two particular kinds of solution. The first solution applies in a situation when we have planar symmetry. The wave depends only on one spatial direction. We have plane waves. And the second solution that we considered, we have spherical symmetry. So you can apply it to a situation where you have waves coming out from a source. If you are sufficiently far away from the source, this is a point which you should remember, that if you are sufficiently far away from the source, so when the wave becomes quite large, you can represent this quite well using a plane. So a spherical wave sufficiently far away can be well approximated by a plane wave. And we have studied only two kinds of solutions. There are a variety of other solutions possible in different situations. You could have a cylindrical solution, and whatever, you could impose different kinds of symmetries and get different kinds of solutions. So we shall end our lecture here today and move on to something new.